as you can see, we can already see the image that is being shared by Omar, who is hosting the event. So, as we all know, will be talking about the latest images that have come in from the JWST. And Mr. Hassan, if you would kindly please
the James Webb Telescope.
Yeah, Shiraz, check out the mutation or mute of every participant, and also at the same time, I want to showcase picture of James Webb Telescope. Can we have the picture of James Webb Telescope, please? Omar? Omar with us?
Yeah, Omar is with us. He's just changing the images.
No, I need a picture of the telescope itself. Okay, everybody. Thank you, everybody, for joining this forum, inshallah, on online. And today, as Shiraz was saying, we will discuss about the James Webb Telescope's first results. So I want to give you a bit kind of historical background about this whole thing. Starting to bring you back or bring from the history, the process of making space-based telescopes. There were scientists in 60s, they were talking about how to make a space-based telescope and what would be the advantage of such kind of a device in the progress of astronomy and field of cosmology and learning and pushing the physics of what we know today to a new boundaries. The vision came for a long time back in 50s, where scientists were dreaming or talking about like Arthur C. Clarke, a famous writer, British writer, who also portrayed a concept that we can send a telescope into the space. And for people who are not aware of the advantage of putting the telescope in the space, just to say it this way, that the atmosphere which surrounds the Earth cut down the useful data which we need to capture from the space by factor of 60 to 70%. I mean, some of you would say shocked that, but we still see the beautiful images coming from the ground station. The problem is that the amount of filtration which happens to the light is so much that the information which we need, they are being cut down. So let me just specify those particular things. First things, we don't get the infrared. Why we don't get the infrared from the spectrum? Because there is a water vapor in the atmosphere, and water vapor, they are very good at absorption of infrared lights. Then we have other elements in the atmosphere which cuts again more and more of the spectra till we reach to the level where the amount of atmosphere and the turbulence in the atmosphere and dust in the atmosphere and moisture in the atmosphere and the heat of the atmosphere and dynamics movement of the air, all of these elements cut something from the light, from the intensity of the light, from the quality of the light, from the spectra of the light. So what we get on a ground-based telescope is something mutated. It have to be rectified. It have to be furthermore filtered, adjusted, and then we get the right picture. So it's not a straightforward concept that you put a sensor, put it on a telescope, and you look at the sky and you get beautiful image. The idea here again, we are not talking about beautiful image as much as we are talking about image which is data, filled with data and information. And here's another topic which I want to emphasize on. What amount of data and how we get the data from the telescope. Okay, imagine this as a message in a bottle. First thing, when you receive the message itself, the bottle, Is it intact? Is it broken? Is it intact? Is it been mutated somehow? We have to see how the message is being received. Is the packaging correct? If that is correct, then we go inside and then we look at the data. Is this right amount of data? This right kind of data which we're looking for? Is it the thing is containing the data, or this grumbled, or it's not working, or the data is not correct? The quality of the data, the quality of the packaging, and all of this information which we're talking about, this is exactly the same analogy we apply on the light coming from the stars. So what things we are looking for? First thing, we are looking for the intensity of the light, luminosity of the light, how bright it is, how good it is. Then we'll go inside the light itself. Do we get some sort of activity over the light? Means, for example, light is more driving toward the infrared or red, or going more moving toward the ultraviolet or violet, because this motion will indicate to us the body is going away from us or it's coming toward us. Okay, so this is very information we get from the intensity of the data itself. Okay, what else? Then we probe inside the data what we are looking for. As we know, the best view of the universe comes from the infrared areas. Why from infrared areas? Because they are able to penetrate the clouds of hydrogen. And we can see the hydrogen in best view in the infrared. So what about the X-ray and others? No, they are more energetic. So they don't show a very clear picture of the universe as much as they show us a general picture, a high energy picture of the universe. And we need an areas of low energy, where are the clouds, the proto planets, exostar, exoplanets. So many things are there. Now, all of this in the light, yes, the light also tells us if there is some motion is happening, some chemical reaction is happening, so much things, information, everything comes packaged inside the light itself. Now, one of the ways to really receive the light properly is to make a bigger telescopes, more wider area to gather the light. Okay. Second thing, add to it more sensors so we can analyze the light immediately while we're receiving it, and then storing it, sending it to the Earth and all of that. Now, going back to the eras of 50s, so the first obstacle was how to really get rid of the problems of the atmosphere. So the answer was very simple, go to the space. Oh, okay, so let's build a telescope in the space. The technologies of 50s and 60s allows us to think in a very, that era style, means the technology which was available at that time. So the scientists were able to configure Hubble Space Telescope. Hubble Space Telescope was made in 70s, commissioned in 80s, launched at end of 80s, and worked from end of 80s till now, and serviced 5 times. But let's remember, the expectation of observing the universe from Hubble was the first, it was the pioneer. It was not something we've been done before. So the pictures of the Hubble were for us kind of, okay, a picture could take 1 week to be analyzed, prepared, and then displayed. What else? It used to have old machines, not like new computers and servers and new sensors and all of that. Though after so many repairs, things become better with Hubble Space Telescope, but the size of it was limited by 2.5 meters. One mirror, 2.5 meters in the space, and that was it. Now, with those things, it posed over us, over the scientists, scientific communities, to do things in a very old-fashioned style. Where when we launched the space telescope, like Hubble, we learned a lot from it. And as they say, for every question we have answered with a space telescope Hubble, there were 10 more questions waiting for a new telescope to come out for it. So our requirement for a new telescope came up very much visual after launching the Hubble Space Telescope. While the Hubble Space Telescope was on the Earth, not yet launched, the talk about James Webb were there. And it was starting to formalize the idea of James Webb Telescope. And it did. At the end of the 80s, 90s, James Webb Space Telescope idea formulated properly, and it started to come to visualization for scientists, and then converted to a project, and then got the funds from NASA. And it's almost sitting for 25 years to develop different types of technologies, tackle to every challenges it might face, and then launch this mighty telescope. Now, let's remember the size of it. It's almost like 6 times bigger than the Hubble Space Telescope. And it is not roaming around the Earth. It is in Lagrange point 2, where it's been shielded, as you see in the picture, from the down plane of this membranes, which are a kind of mylar foil type, which is preventing the heat of the sun to affect the upper portion of the telescope and maintaining its temperature in somewhere in minus 200 degrees. Now we are talking about minus degrees, yes, because you see the glass of the mirror of this telescope is made out of gold plated, not silver, like the Hubble Space Telescope. Okay, so why we are going for the gold plated? The gold is best reflector for the infrared light. Okay, what we learned from the Space Telescope of Hubble, that we were able to look from a different spectra, but we were concentrating on the visual. And what we learned from Hubble, that the best picture which universe gives us through the light which is best available, which can tell us most information, is infrared, not the visual. So we learned from Hubble Space Telescope that's better for us to make the telescope, the next telescope should be infrared based. Like Spitzer's, yes. Like the one which looks through the clouds, through the nebulas, yes. The one which can show us energetic areas and also a less energy area, yes. The areas where we can see planets, yes. The areas where we can study new stars, yes. The areas where we can see the explosion or after explosions, yes. Oh, so everything we can almost see in infrared, yes. The window of infrared far, 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 far wider than the visual. So let me give you a kind of example. If out of 100%, 90% of the view, of the best view of the universe is in infrared, only 10% is visible, is available in the visible light. So it have to be our next telescope, which is James Webb, will be made out of or the range of the infrared. And that's why we made it everything in infrared. All the systems, all the facilities, all different types of mirrors, sensors, all of them works perfect in the infrared. And that was the beauty, which we first made it available for ourselves and developed technologies to put in this telescope and made it really kind of out of the box technology. Very unique technology was implemented to the level that scientists developed it fresh hand. Means the technologies which is applied to the James Webb telescope, it's not technologies of 90s, though it's a design of 90s, but the technology which is implemented in the telescope is technology of today, of 2022, 2021. Sensors, communication devices, computers, backup systems, power systems, whatever you want to say, it's the latest technology. And that's what took all the time to launch this sophisticated, build this sophisticated machine, check it out properly, and then launch it. Okay, now let me start with you again to put things in perspective. First thing, we have to develop it. Development took almost like 20 years. Now, it's not only enough to have developed. Now we have to launch it. So we have to capsule it, encapsulate it in such a way that we can put it in a rocket and send it to Lagrange point. Exactly. This was the next level. So they properly folded it, maintained all the backup systems so they can unfold it without any problem, and put it on the head of the rocket, send it to the Lagrange point, which is where the telescope will stay for the rest of its life. No chance to repair it? No, no chance to repair it. Everything have to be checked and rechecked and rechecked. And now continue with me. Then we have to launch it. Now it takes time to launch it from the Earth to the Earth orbit to moving it to the L2 location. Once the telescopes are launched out of the atmosphere into the orbit around the Earth, it have to do sudden maneuvers, sudden ideas, so it can get sudden things, so it can prepare itself to launch to the L.2. All of that worked successfully. Then the maneuver was launched to send it to L2 point. And when it reached to L2 point, it started to open different instruments and different modules over the telescope. Now, it is one of the most sophisticated telescope ever been built by humankind in different aspects. Now, it's not enough that we should deploy the telescope, open all the aspects. We have to also check it out if it's been deployed properly or not, because we cannot go and reopen something didn't open, for example. So it have to be done in such a way that we get insurance that this thing really makes up. Shiraz, when was this telescope was launched? Month of January, correct? Right? Correct me if I'm wrong. Now, from February or January till now, what the telescope was doing? Oh, opening different aspects of it, different instruments, fixing it, calibrating all the different aspects of the work. And then after that, checking, rechecking everything, it's been opened properly. Then, after everything were opened and become in its position, now they have to do what we call the calibration. Calibration means what? Every instrument should be working exactly as it is supposed to work with. Now we're talking about telescope. So it's not enough that this is not a one mirror system, it's 16 mirror system. It have to be adjusted in such a way that each mirror is aligned with the next and all the next to it, and they can produce for us one single image perfectly. Okay, so this is step one, calibration. After the calibration will be done, we'll get the first image. From the image, we know if there is some flaws, and we're going to go back to the main mirrors, readjust it till we get the right alignment. Once we get the right alignment, then we get another picture where we're going to judge on the picture if every mirror producing the right picture, or these pictures require rectification. Sensors who are working, are they working properly, or they have to be modified, or up and down, calibrated, whatever. And so instrument after instrument after instrument have to be calibrated, aligned, till we get finally assured that the telescope is, according to our functionality, working fine. And then we get to get the images. Now the images which we're going to get are going to be raw images. What is the raw images? The images usually what we get from the telescopes, we call them raw, means nothing been modified. It is just simple image. No filters, no cleaning process being applied till now. We're just getting the image as it should be. After we receive the image, then we start to put things in perspective, means filter it, remove the noise, remove all the, let's say, garbages or unwanted things. Then after that, modify it in such a way that the light which we need, it has to be emphasized. And then after that, false color it. Remember, we are not looking anything in a colorful. So the color have to be added to make sense for our human eye and make it beautiful. And after that, again, apply some few filters of sharpening or unsharpening. And so many other things have to be done to the image, so it become the image which we like. Omar, can you show us the first image?
Sir, actually, because we had started the meeting a little earlier, we are almost out of time on this session. So what I'm doing right now is I'm pasting another link in the chat section for all those that are available over here. So the next session, we will start off by 7:35.
Okay. Thank you, everybody. Prepare your questions. Inshallah, we'll be
Uh,
answering it in the second part of it.
Yeah. Now, sir, in regards to what you were asking for the telescope, my mic was muted when I was giving the answer.
No
It was
problem.
in December 2021, and Satrajit also mentioned it was
Thank
in
you,
December.
Shazad.
It was on the 25th of December 2021.
Perfect.
Nevertheless, I think this is a good time to take a break,
Sure.
and we will resume this session at 7:35.
Okay, everybody, let's start again. So this was one of the images, one of the first image which was received by the telescope, and this was also announced by President President Biden when they were having press conference on this and the release of this image.
Sir, your volume is very
low. Okay, let me check it out. Now, Shiraz, it's okay?
Sounds good.
Okay, perfect. So this picture donates the first image officially released by James Webb Telescope. Okay. First thing what I'm going to do is explain to everybody that this picture, what was my impression when I looked at it? When I looked at this picture, I said, wow, did they do this first thing? I mean, why did I say something like that? I said something like this because of the following. Hubble Space Telescope, it didn't take such kind of picture at the beginning. It took it after years and years of modification, and it came after a while. What this picture is basically about. Let's remember, the Space Telescope, Hubble Space Telescope, took a picture of deep space, a deep space picture where Hubble Space Telescope was pointed to look at a very dark area in the space where usually normal telescope doesn't see anything. And in that area, it opened its shutter for very long duration, 500 hours. Then it got what we called the deep space image of Hubble Space Telescope. And it showed something similar to this, but a bit more blurry. When I saw this image, I said, no way that James Webb will take the first image, this one. So how much hours they have made on that? And when I was reading the caption, I was surprised to see that this was only a few hours. What? Few hours of exposures? What took 500 hours by Hubble Space Telescope? This guy did it in 3 hours. That was one shaking knowledge for me. Now let's probe into, or let's dive deep into the picture. This picture is so beautiful. By the way, it showcased, forget about, do you see this sparkling like ray-oriented? These are the stars in our Milky Way. The rest of that, everything else is the galaxies. Oh my goodness. So we're looking at galaxies. All of this picture is containing galaxies, yes. Galaxies, and not only any galaxies. Imagine with me that you have a biggest telescope in the world, and then in front of that telescope, you put another lens to showcase even dimmer things, which is coming from furthermore back. Oh, wow. As if somebody have given us extra magnification over the current capabilities of James Webb. You see, this is the lens which I'm talking about. And do you see this mutated linear shaped galaxies, or just like kind of mutated shape? Like,
stretched out.
Exactly. Now look at this. It is not a nearby galaxy. It's furthermore far away galaxies than what we are looking at. Wow. When you zoom in, every small speck of dust is a galaxy. Wow, man. We are looking at a picture of billions of words and data. Now we are really looking and probing in time, where we are reaching to something like 13 billion light years away. Oh my goodness, how it's amazing. I'm speechless. When I saw the picture, I became speechless to really, I didn't anticipate to see first an image like this. Second, when I saw the image with this all data and information, I really cashed my head. So this picture is a very, very, very unique and very, very wealthy of data and information. And it can show me now, or we can expect properly what we can predict to see next from the James Webb Telescope. Wow. Now, as we can say, this is the telescope, the dream telescope we have in our hand, which can showcase to us things from the universe which we didn't even dream to see. I will stop at this stage in this image. Go to the next one, Omar. This is another picture for galaxy areas where we have 4 galaxies, 1, 2, 3, 4, and this is a 5th galaxy. This picture was taken by Hubble Space Telescope, and the new one was taken by the James Webb, just to make a kind of a comparison between the 2 images. This image, it was more as a blobs in the Hubble picture. Now we can see the details of the galaxies, the details of the material which is spreading by the galaxy and affecting each other, and showcasing to us how the 4 galaxies are interacting together, plus this galaxy also, plus whatever the backgrounds. And it definitely, with more analysis, will show us the effect of the dark matter and dark energy into this. And easily we can see the material distribution into this field. I don't want to talk about details more because there is lots of, again, information here, all the way background between all of this and the different aspects of it. More filters we're going to apply to see the more deep and more distribution of the material. We're going to extract more information out of this picture. Next image. Now, this is part of Carina Nebula. Any person who have seen the Carina Nebula, it's a one wealthy area in the space, jam-packed with action. And this is portion of Carina Nebula. And as we see these stars, what you see here, they came out of these clouds. But see something, there are clouds even in front of these stars. So where are these clouds? These clouds have gone due to that we are looking at infrared images. So infrared images showcasing to us the hidden portion of the Carina Nebula. You see this blob because of these stars, this winds, solar winds, which is pushing these clouds in this shape. So all of this is affecting this area and creating distribution of hydrogen gas in different concentrations. So we can see the gas and how they are moved away from the areas where the new stars have came up. And too much information. Look at the corner of it, the stars, the other corner, the stars. I mean, this beauty, if you compare it to the Hubble Space Telescope, would be very kind of dull image comparing to this detailed and fine detail of stars and number of stars, clusters, super clusters, parts of the combination of action which is happening in this cloud. Next image. Yep. This is another picture which was taken by Hubble. But in the picture of Hubble, it was very dull. And I myself tried to zoom into it to find some details. I was not able to find much of details. This image really surprised me and showcased to me so much beautiful. I can compare it to the detailed image which was taken for Ring Nebula by Hubble Space Telescope. Amount of details came out when they combined 3 different filtered images, like for example, infrared, the visual, and ultraviolet. It came with so amazing detail, but this image alone having more than the details which Hubble was to make it out. And clearly you can see the central star which exploded out and created for us this beautiful ring type nebula which we see. Again, I'm not explaining the details and technical details about the image. I'm morely describing what I can see from the eye, the beauty of amateur astronomer who loves astronomical pictures, and he can make some sort of simple senses. Again, I cannot stop probing inside it. You can see the galaxies here and here. You can see so beautiful things in the background, and how amazing this structure we made with the explosion. It tells us that the universe have a beginning and also an end. And this new device is showcasing amazing different chapters, different places, different times, different actions in the space as we probe on with our new telescope. And with this, I would like to end my talk, but also I would like to announce something which, Omar, I would like you to take in consideration. There is a new movie, 2 movies I have downloaded from the internet, and it will be available in our Astro Cinema, around 1.5 hours, running both of them. These are from PBS and YouTube. I would definitely invite you all to come down to our center and see this film. It's a very informative and very much I would love everybody to look at it. Please come down. And as you know, the Astro Cinema is free for our members, so they can come at any time and inshallah see the films. And for non-members, you can either avail the membership or come down, and for 10 dirhams you can see almost like 2 hours of James Webb Telescope, all the details, all the information. Adding to it, the details of the new images have taken and been narrated by renowned astronomers who are explaining the images furthermore. And with this, thank you everybody, and back to you, Shiraz.
Thank you very much, sir. Thank you very much for that explanation. I'm just telling everybody that if you have any questions here, you can ask them in this chat. All right. So, sir, I actually have a question. So these images that we're seeing and these colors that we're seeing, given that the JWST is an infrared telescope, how exactly are these colors real, or what's happening?
Okay, the colors are being false. These are all false color. Combination of different filters, we got this kind of details. Let's remember, as we have regions in the visual, the 7 regions, different types of frequencies give you different color. Here we are opening the infrared area. Just for your, I will do a sort of comparison to showcase how big is the area of the infrared. Now I'm holding in my hand a pen. Everybody see the pen? You see, if I'm imagining, do everybody see the pen? There is an area of the red. Yep. Let's imagine this area is the visible area. So the infrared is the one which is the white one. So the infrared is much bigger area than the visual one. So red infrared, the infrared area, I can make it sub areas, and every those of areas I can take it with specific filters, and with this specific filters I can recolor them with different colors to create those kind of impression colored image. Though the real image is mostly for our eyes, it would look like black and white because we don't have infrared sensors in our eyes.
All right, sir, we have 2 questions here from Satrajit. Number 1, why did NASA send gold plated mirrors? Wouldn't that be more heavy and costly?
Okay, the gold is not, it's plated. Remember the word plated, not made out of the gold. What does that mean? That when we make a mirror, we coat it with a layer of either silver or gold. Gold for infrared. We need to capture the infrared. Gold is more reflective to the infrared than the silver one. Now the weight of the whole total gold is not that kind of the weight which we are talking comparing to the telescope. The telescope is something like 4 tons. The weight of the telescope. So and in the space, it doesn't make any differences actually, because we know the space is weightlessness.
Secondly, sir, if I can just come back to the question, just a second. Yeah. So the second question is, why are the stars in the deep field image? Why are the stars 6-pointed?
Because of different filters applied. Number two, they are after effect of processing. Means these things will happen because the concentration of the scientists are in the background, not on the foreground. So these artificial effects comes out while we are trying to emphasize other things. And these are areas where light are saturated. Saturated means a lots of light coming up. So we need to reduce it by putting some sort of masking. So scientists are putting masks to reduce amount of light from the stars and to enhance the background image. So these we call it after processing effects.
The next question we have is, why did they choose Lagrange point 2, not 1, 3, or 4?
Okay, Lagrange points are distributed in such a way that imagine with me the Earth, an Earth orbit around the sun. So where is the Earth? There is 4 points. The 1 is toward the sun, 2 at the back, 3 at the front, and 4 is at the back. And 5th is the other side of the sun. Again, imagine the Earth orbit, imagine the Earth and the orbit around the sun. So the Lagrange point 1 is toward the sun. So let's imagine that this is the Earth. This is the Earth.
Omar, can you share an image of the Lagrange points?
So 1 is here, 2 is here, 3 is here, 4 is here. So we want to be in an area where sunlight and Earth heat should not affect the telescope, absolutely. Any more questions?
Yes, just a second. I've actually just requested Omar to share the image of the Lagrange points to make the explanation much more easier. Nevertheless, we'll just quickly go to the third question. Fourth question. How do they manage to make the mirrors fold, and why are they divided? In the sense that, yes, this is the image of the Lagrange points, sir.
Yep, exactly. Perfect.
So
L1
as you can see, where L2 is away from the sun, L1 is towards the sun. And
exactly.
That's where the...
Exactly. Now, what else, what we can put in L1? Actually, we already have some satellites in the L1, like, for example, SOHO, observing the sun 24/7. So SOHO spacecraft, which is observing the sun, it is not roaming around the Earth. It is in L1 point.
I also believe Helios is doing the same thing.
Helios spacecraft is also doing studying the sun. There is L3, for example. There is other missions are being there to observe the sun from other side, like, for example, Stereo mission was observing the sun from different aspects, from different places. So every Lagrange point, scientists, they are using it for different types of research and studies of the universe. Okay,
right. So, yeah, once again, the question, how did they manage to make the mirrors fold, and why are they divided? Or I'm assuming what he means is, why is it a segmented mirror system?
Okay. Scientists found out at the 50s and 60s that there is what we call weight problem with the mirrors and how big you can make it. And the biggest mirror was made was 5 meters at that time. Hall telescope, which was in Palomar Observatory. They wanted to make bigger mirrors, and they had a big problems. Gravity really plays a major role to what we call it, deform the telescope and it become useless. So they come to an idea where bigger mirror was posed, but not in one piece, but in segmented piece. And the idea was very good. Each segment would be behind it some mechanism to make it move in 3D. So this movement allowed that we can create segmented mirror system where we can align them all together and create one mirror concept. And it was successfully made on the Earth. For example, we have at the observatory called Keck observatories, Keck telescopes in Hawaii, 2 of them. Similar way with 3 telescopes in ASOS, European Southern observatories. And similar to that, there is a project for making 30-meter telescope segment. And there is another project called 100-meter telescope. All of that possible because of segmented mirroring or segmented manufacturing facility of the gigantic telescopes. This segmentation allowed us to go beyond what we really thought that the telescope could be made. So James Webb used the same technology, which is well crafted and well known and highly controlled. Now, it was not just because of the size we wanted. Second thing, the reason why we went for segmentation is that we can make it 3 pieces, 1 central piece, 2 side pieces, where side pieces can be folded and then brought forward, and all create for us the 16 segmented mirror-based system. Now, why we want to do that? Because you see, the rocket nose is not a very big area. The total area is around 5 meters is there. You have to put everything in that cone shape, okay, in a 5-meter diameter, and that's it. So how are we going to put this 16 mirror-based telescope inside that 5 meters? You have to segment it into pieces, 3 pieces, and then fold it. And then when we go to the space, we unfold it and bring the things exactly as should be. You can imagine Hubble Space Telescope was 2.5 meters, which was in the exact size where the space shuttle was made for. The bay in the space shuttle was made in such a way that it takes in consideration that one day it will take space telescope to the outer atmosphere, to the outside of the atmosphere. This was one of the reasons why shuttle was designed in such a way. So it can take almost like 2.5 meters. But imagine if shuttle today is there, it cannot take the James Webb telescope mirror there. So how to do it? Again, we get back to the drawing board and we create segmented systems which we can be unfold, fold, and we can take it to the space. Any more questions?
Yes, sir. So Kamil wanted to point out that the 6 lines in the stars is due to the diffraction of the 3 mounts. Basically, the 8-pointed stars that we see is due to the diffraction. Question from Ritu is that if the James Webb Telescope can capture such deep space images, can it also zoom into other stars which have planets in different galaxies?
Okay, this is a big challenge, but possible. Possible because of the James Webb resolution, which can allow us to even detect planets in, for example, like Andromeda Galaxy, very close galaxy, or even in the Large Magellanic Cloud, the small and the big one, because these are satellite galaxies, the last 2, and we can really observe many things into them. So finding exoplanets in them, that would definitely possible. But what it did actually, James Webb did in the few weeks back, it did measure the atmosphere composition of exoplanet, and it found clouds of water. And that was awesome, almost like 1,000 light years away from us. I mean, this was such a beautiful spectra, I would say, that confirmed immediately that we can see the clouds in the exoplanets. Oh, wow. The next step will be more surprising. Can we really detect any kind of gases which will be produced by the life? That will be the best news we're going to hear. Yes, life is everywhere.
Right, sir. So these are all the questions that we have so far. If anybody has any more questions, you can send it to astro@dubaiastronomy.com. This is the email address that we regularly check. If you have any questions that you wanted to ask but could not or later realized, please feel free to send them on astro@dubaiastronomy.com. And keep an eye on our social media and on our website, because we have quite a few programs coming up towards the end of this month and the month of August. And obviously September, October will be very, 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 very busy, considering that October we have the solar eclipse as well. And we have some of these space camps, the astronomy camps that we will be having for children this coming week, and also the stargazing parties and the training programs that we are hosting. So a lot is happening. I would highly recommend everybody to keep their eyes on our social media and on our website to be constantly updated about all the upcoming events. And we look forward to seeing you guys soon. Once again, Mr. Hassan, thank you very much for your time.
Thank you.
And for this wonderful explanation. Kamil also says thank you very much for the talk.
Thank you, Kamil. Thank you.
Larissa also says thank you so much. Right. Thank you very much, everybody. It was a pleasure. And we hope to see you guys soon. And with that, I would like to end the session. Thank you. Thank you. Bye-bye.
Thank you. Bye.
Okay, bye, everyone.
Bye.